In this lecture, we will talk about update and delete query statements and how we can update data in tables on SQL. Update and delete query statements. Update basically means transforming any null value in a column by adding a value to it. Or it could be that we added the wrong values in a table and now we want to remove them and correct them. In these situations, we can use the update statement. It is mainly used for modification and updating of existing records in a database table. Quickly, while I think about it, I wanted to tell you one more thing. As you may have noticed, I'm moving my cursor towards the execute button again and again. But if I hold the cursor on the execute button, it shows us information about F5. This means that we can also execute our queries by pressing the F5 key. I should have told you this in the first lecture, because I actually use the F5 key to execute. I find it much faster than clicking on the execute button, but it's a personal preference. Anyways, parenthesis closed. Back to our update key. Suppose we want to add value in the null price column of ID number 5. We will execute the following update statement. Select star from book_detail, update book_detail, set price equals 4000, where ID equals 1. When we will execute the query, our data will be inserted in a table. By using the same process, we can update all columns one by one by using an SQL table. Now, if you see a table on the screen, there are two tables for platform, and we want to delete a column of our platform. To delete a column, we will use the drop word in query. We use the drop word in SQL to delete things in a table. So, we run the following query. Select star from book_detail, alter table book_detail, drop column platform. Now, if we click on the execute button, the platform table will be deleted. If we wanted to delete any table, we would have two options for that. One is to move the cursor on the table, right-click on it, and select the Delete button. Or we can run a query. If we want to delete a table by running a query, it would look like this. Select star from student 1, delete from student 1. Now, if we click on the execute button or F5, the table data will be deleted from our database. Now, if we press the refresh button and open the table of the database base, we can see that the table student 1 is not displayed because it has been deleted from the database. Like operator. Our next concept, after delete or drop, is the like operator. In this category, there are two types of operators. Number 1, light operators, and number 2, wild operators. Wild operators are similar to light operators, but with minor differences. Mainly, we can increase corrections in wild operators. As you can see on the screen, I have used A and C alphabets, but it doesn't mean that we can only use these two alphabet characters. We can use any character from the 26 letters of the alphabet. So now, let's look at the first like operator to see what it means. If we write the following query, select star from sales, where customer_name, like, open quotation marks, C percentage sign, close quotation marks. Customer underscore name is the column, like is the operator, and C percentage sign is a condition in the above code. As we have already discussed, you can use any letter instead of C from the 26 characters available. Now, to come back to our condition C percentage sign. If we use the percentage sign after a character, it means that we can execute the query and it will show all the names starting with C in a table of customer name in the sales table. We currently have 10 records in our sales table, and only one record starts with a C. That's why it's only showing one record, that of Carlos. If we now run the following query, select star from sales, where customer underscore name, like, open quotation marks, E, percentage sign, close quotation marks, it will show us the records in the customer name column that start with E. Once again, we can use any alphabet letter from A to Z before the percentage sign. Now, we will learn about the second like operator. Let's run the following query. Select star from sales, where customer underscore name, like, open quotation marks, percentage N, close quotation marks. Now, if we execute the query, it will show us the records in the customer name column ending with an N. We have 10 records, but only 3 records end with the letter N. That's why we can see on the screen the data for Pyman, Allison, and Hilton. Simply put, if we write characters before the percentage sign, it will show us the names starting with the character we specified in the query. And if we put our letter after the percentage sign, it will show us those records that end with that character. Now we will tackle our third like operator. If we run the following query, select star from sales, where customer underscore name, like, open quotation marks, percentage sign, MA, percentage sign, close quotation marks. Now if we execute the query, it will show those records in which the letters M and A are together from the customer name column. If we execute the query, it will show the record of Pyman, because M and A are together in Pyman. If we now run the following query, select star from sales, where customer underscore name, like, open quotation marks, percentage sign, OR, percentage sign, close quotation marks. Now if we execute the query, it will show Taylor, because O and R are together in that record. Now if we use A and L in a condition of the above query, it will display 2 records, Alfred and Allison, because both letters are together in those 2 records. So that's how you can rapidly identify records containing certain letters and/or in certain positions. Now let's see our fourth like operator. Let's try the following query. Select star from sales, where customer underscore name, like, open quotation marks, underscore, C, percentage sign, close quotation marks. Now if we execute the query, it will show the record in which the letter C is in the second place in the customer name column. For us, it's not showing any result, because there is no record that matches our query in the customer name table. If we replace C with A in the above query and execute, it will show the records of Carlos and Taylor, who both have an A as their second letter. This like operator means that we can show a record for which A or any used letter is in the second position. Now we will see our fifth like operator. If we run the following query, select star from sales, where customer underscore name, like, open quotation marks, J underscore percentage sign, close quotation marks, we will see the record in the customer name column starting with the J character, but that also have at least 2 extra characters. Technically, it should show us a word starting with J and other extra characters. With our data and records, the result Joe appears because the record starts with a J and also has more than 2 letters after the J. This query will not show any result if there are less than 2 characters after the J, which will cause an error. Our next like operator is similar. Open quotation marks, percentage sign, underscore, C, close quotation marks. But in this one, there should be at least 3 more characters after the chosen letter. We are using C, which means there should be 3 characters after C in a word. Otherwise, it will cause an error and it won't yield any results. Our last operator is run with the following query. Select star from sales, where customer underscore name, like, open quotation marks, A percentage sign C, close quotation marks. This query will show the record in which the word starts with an A and ends with a C in the customer name column. But for now, it's not showing any result because there is no record which fulfills these conditions. If we change it to P percentage sign N in the previous query and execute, we will see the result Pieman because the record starts with a P and ends with an N. These are some like operators with which you can check records and sort them by defining conditions according to your convenience. Now the question is, why do we use like operators? Like operators are very useful to find names with specific patterns in an SQL server. Such operators are necessary when we work on advanced levels usually. In the next lecture, we will learn about wildcard operators. In the last lecture, we studied like operators, which are used to find patterns of records in a database. Now we will learn about wild operators, and we will also discuss how to use them in our database. I just want to tell you the basic difference between like operators and wildcard operators. We use like operators to find or specify records in a column through a specified pattern in a where clause. A wildcard operator is used to substitute or replace one or more characters in a string that we have found with a like operator. So, there is a relation between like operators and wildcard operators, because like operators just follow a pattern chosen by us, whereas a wildcard will create its substitute and find the record for which the pattern occurs. Wildcard characters include /*, percentage sign, underscore, open square brackets, close square brackets, circumflex, and */sign. The percentage sign is used to find 0 or more characters. The underscore is used to represent single characters. The square brackets are used to represent a single character within the brackets. And the circumflex represents any character that is not in a bracket. Now we will run them one by one with our queries. As you can see on the screen, there is the record of Carlos in the table. We will create a pattern for it by using a like operator with the following query. Select *from sales, where customer underscore name, like, open quotation marks, ARL, percentage sign, close quotation marks. SQL will follow this pattern and it will find the names related to ARL for us in the database. If we run the above query, it will not show any result because, according to the conditions added, Carlos does not start with ARL. So we need to make a little change. Select star from sales where customer underscore name, like, open quotation marks, CAR, percentage sign, close quotation marks. Now, it will show the names starting with CAR. Carlos appears in the result because it starts with the characters CAR. If we use the following query, select star from sales where customer underscore name, like, open quotation marks, PIE, percentage sign, close quotation marks, it will show Pieman in the result because it is the record that fulfills the conditions of the query. So this is the method to see records based on specific patterns. After this, we have the underscore wildcard character. This character can be used to find specific characters and their place in the record. For example, if we want to find Taylor in our records, then we will run the following query. Select star from sales where customer underscore name, like, open quotation marks, T underscore Y underscore OR, close quotation marks. Now we have tasked SQL with finding the record whose first letter is T, the third letter should be Y, and the last letters should be OR. Now we execute the query and we see the result, Taylor. Another one to practice. If we want to find Roger's record, we will use the following code. Select star from sales where customer underscore name, like, open quotation marks, R underscore G underscore RS, close quotation marks. Now if we execute the query, it will display the result, Rogers. Now we will use the square brackets wildcard. We will define specific letters in between the brackets and the result will be shown according to the letters we have used. The following query is an example. Select star from sales where customer underscore name, like, open square brackets, A, B, D, F, G, I, J, L, close square brackets, percentage sign. This query asks SQL to only show the records which start with the letters specified in between the brackets. Now, if we execute the code, it will give us the result Joe, Alfred, and Alison, because J and A were mentioned in the brackets. If we added a C in the brackets, it would also display Carlos, because it starts with a C. If we had P, it will also show P characters, and so on. Now we will use the circumflex wildcard character. Run the following query. Select star from sales where customer underscore name, like, open quotation marks, circumflex, capital A, C, capital F, percentage sign, close quotation marks. This query will show all the records except the records which start with the letters A, C, and F. Now let's see another wildcard character, dash, which is used for the purpose of a specific range. For example, we can use the following query. Select star from sales where customer underscore name, like, open quotation marks, open square brackets, A-G, close square brackets, percentage sign, close quotation marks. It means that it will show all the records whose names are starting with A, B, C, D, E, F, G. It's showing 4 results which are related to our query. Now if we run the following query, select star from sales, where customer underscore name, like, open quotation marks, open square brackets, A dash Z, close square brackets, percentage sign, close quotation marks, it will show all the records from A to Z. That's all on how to use wildcard characters by making patterns. In this lecture, we will learn about constants and how we can use constants in SQL. Constants are basically used to apply limitations and restrictions in our database. They can be specified when our table is created with a creative statement or after. This means that we can specify some rules and apply certain limitations while using constants to submit our data. There are many constants, and we will go over the main ones. First of all, we will talk about the not null constant. This constant is used to ensure that a column does not have any null value. It means that if we have not entered data in a column, then the data will not be submitted and it will cause an error because of the constant we have defined. The second constant we will discuss is called unique. We use this constant to ensure that all the values in a column are different. If we submit identical values in a column, it will cause an error when using the unique constant in SQL. For example, in our ID column, all of the IDs are different from each other. If we try to enter the same ID, 1, 1, twice in the same column, it would cause an error. The third constant we will discuss is check. Check ensures that a condition applied in a query is true or false. For example, if we created a column with data on age and applied limitations of age, for example, that only 18 plus or students above 18 years old could be added in the database, students with an age below 18 would not be added into the database. I will soon show you practical examples of the first 3 constants. But before that, let's talk about default. Default programs a default value to fill in a column if no value is specified. For example, we make a column in a table from our database and add some values in the default constant. Then, if we leave the column empty and submit it, the column will, instead of being null, be submitted with a default value that we set. The next constant is the create index, but we will see it later because it is a lengthy concept. Let's first do some practical examples of the constants we have already discussed. So first of all, we want to create a table with the name school, and we will give ID as integer and give it a primary key. Primary key and foreign key are also constants, which we will discuss in an upcoming lecture because their role is very important. For now, let's use not null instead of a primary key. It means that we cannot submit a null ID. We always need to add a value in it. Now let's add username and use varchar characters with the limit of 20 and add the constant unique. This constant means that no user will be repeated twice in the same column. Each data must be unique. We could also use the unique constant in the ID column. Now we will add the age column as integer, and we will add the check constant in it, with the limit of age greater than 18. You could also add more limits if you want, of course. That's up to you. Now we will define class with Wildcard characters that are limited to 50 values, and we will set a default value, new user. The query of this constant is as follows. Create table school, open brackets, ID int, not null unique, user underscore name, varchar, open brackets, 20, close brackets, unique, age int, check, open brackets, age greater than sign equals 18, close brackets, class, varchar, open brackets, 50, close brackets, default, open brackets, open quotation marks, new underscore user, close quotation marks, close brackets, close brackets. Now we will execute the query. We see on the screen that the query was executed successfully. Now, let's select the table. For this purpose, we will add the query select star from school. Now we execute the query. It is not displaying any results because we have not submitted any values in our data. To insert data, we need to run the query insert into school, open brackets, ID, comma, username, comma, age, comma, class, close brackets, values, open brackets, 1, comma, open quotation marks, Alison, close quotation marks, comma, 28. As you can see on the screen, I used the insert key and inserted values of ID, username, and age. But I didn't insert class because I already set its default value earlier. Now let's execute the query, and you can see on the screen that our first row was submitted successfully. Now if I use 1 again in the above query and execute it, it will cause an error that says violation of unique key constraint. This is because we used the unique constant for the column ID, so we can't add the value 1 multiple times. Now if I add the value 2 for ID and execute the following query, insert into school, open brackets, ID, comma, username, comma, age, comma, class, close brackets, values, open brackets, 2, comma, open quotation marks, Ali, close quotation marks, comma, 28, close brackets. Here, we again have an error because we also used the unique constant for username. Now let's change the name and execute the following key. Insert into school, open brackets, ID, comma, username, comma, age, comma, class, close brackets, values, open brackets, 2, comma, open quotation marks, Ellison, close quotation marks, comma, 28, close brackets. It will display the result, and one more row will be added into our table, school. You may have noticed that the age is the same in both queries, but it didn't cause any error because we didn't use the unique constant for it. So this is how you can apply limitations by using constants. Now, if I change the values in query as follows, insert into school, open brackets, ID, comma, username, comma, age, comma, class, close brackets, values, open brackets, 3, comma, open quotation marks, Carlos, close quotation marks, comma, 17, close brackets. If we execute the query, it will cause an error because we applied a restriction on students that are below 18 years of age. If we change the age to 18 in a query as follows, insert into school, open brackets, ID, comma, username, comma, age, comma, class, close brackets, values, open brackets, 3, comma, open quotation marks, Carlos, close quotation marks, comma, 18, close brackets. After execution, it will not cause any error, and the third column can be added to our school table. In this SQL lecture, we will study how we can use the primary key and the foreign key. We will also talk about their importance and the role of these keys for being preferred to combine two tables and submit data with each other. First of all, we will create a new database named admin. Our database is created now. Now, we will create a table with the name user1, and we will use constants. We will use ID as integer and primary key. This means that IDs in user1 will be used as the primary key. Then on the second column, we will use username with varchar characters limited to 50. Then we will use password as integer and user constant not null. Then we will add gender with varchar characters limited to 6, and then we will add age as an integer. The query is the following: create table user1, open brackets, ID int primary key, username varchar, open brackets 50, close brackets, password int not null, gender varchar, open brackets 6, close brackets, age int, close brackets. Now, let's insert values by using the following query. Insert into table user1, open brackets, ID, comma, username, comma, password, comma, gender, comma, age, close brackets, values, open brackets, 1, comma, open quotation marks, Peter, close quotation marks, comma, 85411, comma, open quotation marks, male, close quotation marks, comma, 28, close brackets. We need to select the column in our database. Select star from user1. First, we will run the table query, then execute the insert query, and then we will execute the select user1 query. As you can see on the screen, our table is created now. We can also create more tables by just copying and pasting the above query by changing little bits of data and values. We will just add one more query of foreign key for the purpose of learning about primary keys on the first table, because the primary key of the first table will be referred to as the foreign key of the second table. To do so, we will use the refer table name, which is user1 ID, which is also the parent table query for the second table. This is what it looks like. Create table user1, open brackets, ID int primary key, user1 ID int foreign key references user1, open brackets, ID, close brackets. Username varchar, open brackets, 50, close brackets. Password int not null. Gender varchar, open brackets, 6, close brackets. Age int, close brackets. Now we will insert values as follows. insert into table user1, open brackets, ID, comma, username, comma, password, comma, gender, comma, age, close brackets, values, open brackets, 1, comma, open quotation marks, Carlos, close quotation marks, comma, 85711, comma, open quotation marks, male, close quotation marks, comma, 20, close brackets. If we execute the query, it will cause an error because the name of both tables is the same. Now, we will change the name of the second table to user2 and run the query. Now, our query is submitted successfully. Let's select the columns as follows. Select star from user1, select star from user2, and execute them. As you can see on the screen, both tables are created now. Let's quickly go over something important. I created a table and used some constants to add columns, and then I repeated the same process for table 2, except that now the new column of user1 ID is to recognize the foreign key. Then I had to insert the data one by one. But if you look closely, I didn't add the user ID column. It was inserted automatically in the second table. That's because we used it as foreign key on the basis of reference, and now we just have to add data in it. To do so, we have two methods. One is that we can insert value, or we can use an update query. For this purpose, we will run the following query. Update user2, set user1 ID equals 1, where ID equals 1. Now, let's execute the query, and you'll see that the data is imported in the ID column. As you can see, I just imported one ID. I didn't add multiple data. To test the link between both keys, let's try adding an ID that doesn't exist in the primary key. Let's try adding ID3 with the following query. Update user2, set user1 ID equals 3, where ID equals 1. Unsurprisingly, it will cause the error. The update statement conflicted with the foreign key constraint. The conflict occurred in database blog, table dbo.user1, column ID. It means that there is a conflicted data in user ID that prevents us from updating our statement. Now, if we try to delete some data, we can't do it because we would have to delete the primary key from the parent table for this purpose. So what is the use of the foreign key here? The main objective is that we are able to insert our data from one table to another table automatically. Officially, the use of a foreign key is the foreign constant is used to prevent actions that would destroy links between tables. The foreign key is a field or collection of fields in one table that refers to the primary key in another table. So this is our lecture about primary and foreign key. Hopefully you understand their use better and how to manipulate data and tables with it. In this lecture, I will talk about the concept of join and how we can use it. Join is actually a keyword of three kinds. Number 1, join. Number 2, left join. And number 3, right join. We can join tables by using these keywords. You can use the join keyword if you have a clear understanding of concepts like the primary key and the foreign key. This is because through the join keyword, you can show the data of user1 table data in a user2 table, and vice versa. As you can see on the screen, I already created two tables, and I used the user ID of table 1 as our primary key, and used user ID as our foreign key in a second table. I just gave 4 foreign IDs, which means I gave ID 1 twice and IDs 2 and 3 once. So now, if we want to join both tables, how can we do this? The answer starts by selecting the table we want to join. For now, it is user 1, and then we will run the following query. Select star from user 1, join user 2 on ID equals user 1 ID. If we execute the query, it will cause an error because the system does not recognize these IDs that are related to each other. To avoid this error, we will add another table name with a name and execute the following query. Select star from user 1, join user 2 on user 1 dot ID equals user 2 dot user 1 ID. Now we are able to join these tables because we are using the primary key and the foreign key. If we did not use these keys, we would not be able to join the tables. If we run the above query, it will show the result 1, 2, 3, 1, and it will also show the user ID column. This means that the two tables seem to be joined together. But if you look closely, Peter appears twice, Antonio once, and Amelia once. Because I'm using Peter twice, one time in the first ID and a second time in the fourth ID in the user2 table. If I had used it 3 times, it would be displayed 3 times. If you want the full table to be displayed, you have to add left join in the query as follows. Select star from user 1, left join user 2 on user1.id equals user2.userid. If you execute the query, both tables will be displayed in the result. You can also use the right join when table 2 primary key is used as a foreign key in table 1. Now if you use right join and use the following query, select star from user 1, right join user 2 on user1.id equals user2.userid, it will show all the data of table 2, but in table 1 it will only display the data which is used as a primary key and a foreign key in table 2. If you want to see the full combined data of both tables, you can use full join in the query as follows. Select star from user 1, full join user 2 on user1.id equals user2.user1id. Now if we execute this query, it will display the combined result of both tables by using join, left join and right join all together. In this video, we will talk about an important topic of databases, which is normalization. You can say that normalization is a process or a set of rules that help us structure and organize our data. Before we start this video, I would recommend that you watch or re-watch the video on relationships, because a lot of the elements discussed in that video will be very important for this video. If you haven't seen that video, watch it first, and if you have already watched the video related to relationships, then let's start this video. The main reason to use normalization is to reduce the redundancy or repetition of data. We need to ensure that data is not repeated if we are storing it. Data should be stored in a single place. We don't have to store the same information in multiple places, otherwise it will create problems. That's because redundancy data will take up more disk space due to multiple records of the same data. Multiple recordings of the same data wastes disk space, and it makes it harder to manage multiple records of the same data. We would face anomalies, which are abnormal behaviors, while inserting, deleting, and updating data. For example, as you can see on the screen, the students table full information is displayed, which includes student, ID, name, phone, room, and class. If we look at the class table nursery, 3 and 4 are repeated multiple times. This means that the class column is displaying repetitive data. Let's suppose that we want to write KG1 instead of nursery. Then, we don't have to update one nursery data. We would have to update the 4 records that are related to nursery. Let's suppose one or more of the records didn't update due to an error or a problem. Then, our data would become inconsistent. Now, one more thing. If we delete all students of the nursery class, it will also delete the nursery class. We will call this a delete anomaly, because we are recording one record, but another record which is related to it is being deleted. However, this is theoretical. Let's not do it here. So to solve these kinds of issues, we use the rules of normalization. There are many rules of normalization. The first rule is called first normal form. The second rule is called second normal form. And the third rule is called third normal form. The first normal form says that each table cell should only contain one value. It means that each cell of a table cannot contain multiple values. If we see this with the help of an example, we will understand it better. You will see on the screen that there is an employees table. If we focus on the phone column of the employees table, the first normal form is being violated because the employee with the ID 2 has multiple numbers, and we have added these phone numbers in the same cell. To solve this problem, we have made 2 entries for the employee with the ID number 2 and wrote their phone numbers in different cells. By doing so, NF1 is not violated here. But a problem remains. Because the other data of employee 2 is repeated multiple times, it means that it is using extra disk space and becomes a redundancy data. To solve this problem, we will break the single table into multiple tables, as we have discussed in the relationships video. That's because the relationship formed between employee and phone is a one-to-many relationship. And if we want to organize one-to-many relationships, it's best to use multiple tables. Now, if you look at the screen, I have broken up the table into different tables of employees and employee phone. Keep one thing in mind though. If you are seeing repetitive data, it means that there is a problem in your database design and you must resolve it. Now, because we have a correct design, we cannot just assign 2 phone numbers to an employee, but we can assign as many phone numbers as we want, and NF1 will not be violated. Our second normal form says that 2 conditions must be fulfilled. The first condition is that the relation must have started in a first normal form, that you then move into a second normal form. The second condition is that no partial dependency exists in your relationship. Now let's talk about partial dependency. If you look at the example on the screen, we have 3 tables which include user, videos, and a third one which is user watched videos. We have users who could be users on our website or on YouTube, for example. The website may be related to videos, where users watch videos on the website. In our example, we want to store information on which user watched what amount of videos. A user can watch multiple videos, and one video can be watched by multiple users. So these are many-to-many relationships. We define many-to-many relationships by making a bridge table or a conjunction table. The user watched videos table on the screen is actually a conjunction table. We can clearly see in this table which user watches how many videos, and how a video is being watched by how many users. If we look at the table user ID, the video ID is available, and it also shows the user watch time, that is, how much time a user spent watching the video. Our conjunction table also shows what date the video was watched and the email address of the user. But there is a problem in this table. This table is violating NF2 because NF2 says that there should be no partial dependency. Partial dependency means that attributes, properties, or tables of a column are fully dependent on the primary key. If we see the user table above, we can see that user ID is the primary key, and our name column will depend on our user ID. If we look at the second table, the title will depend on the video ID, and if we add a video URL column, it will also depend on video ID. However, if I add a username column in the video table, it is not linked with video ID, so we cannot add it here. This means that we have full dependency in both tables, but partial dependency means that you have attributes which depend on the primary key, but only a part of the primary key. It is also necessary for the primary key to be composite. This is something we discussed in a previous video. I encourage you to watch it for more information. I will specify that a composite key is a primary key, but it is created by multiple columns or multiple attributes, not by single attributes or a single column. If we look at our user watched video table again, we see a composite key here, which is created by user ID and video ID. This is because user ID and video ID together uniquely identify the records for the table. In other words, user ID and video ID are combined together and make up the primary key. Everything you will insert in this table should be fully dependent on user ID and video ID. They should not be partially dependent on one of them, because we have the problem of partial dependency, not full dependency. If I look at watch time, it is the watch time of a certain video, and that video is watched by a certain user. Therefore, the watch time depends both on user ID as well as video ID. Now, if we look at the email column, it is the email of a certain user, but it has no relation to video ID, because it is the attribute of a user only. The email depends on the primary key, because user ID is our primary key, but not the only one. Video ID is also a primary key, which means that the email column is partially dependent on our primary key. Therefore, the email column is an example of partial dependency, and it should not be present in the table. So it means that we cannot keep our email attribute or column, because it is not fully dependent on the entire table's primary key. How to solve this? Now, if you look at the table, I shifted the email column to the users column, because it is related to the user. And now, we don't have the problem of partial dependency anymore in this table. Now, this table is fully filling the NF2 condition because we only have related things in our table. User information will be in the user table, video information will be in the video table, and in the conjunction table, we keep the information which must imperatively relate to both the user ID and the video ID tables. If I add video title or URL in the videos watched table, it will create partial dependency because the video title will not be related to the user information. This problem only occurs when we are using composite key, because if we are using a single column, then the attribute should be fully dependent on the primary key, or not dependent at all. But partial dependency doesn't even exist. When we are defining many-to-many relationships, we have to pay attention to the composite key and keep our data in related tables. Now, let's talk about the third normal form, which has two conditions. The first condition is that the second normal form should be fulfilled and that no transitive independency exists. What is transitive independency? I'll explain it with the help of an example. If we look at the books table on the screen, we see book ID, title of book, name of author, year of publication, and date of birth of the author. If you look here, our columns author and title have a relation with book ID, because book ID is the primary key. But as you can see, the date of birth of the author is not directly related to a book ID, so it means that the date of birth does not depend on the primary key, but it depends on the author. This is what we call transitive dependency. In other words, it's when your attributes don't directly depend on the primary key, but depend on other attributes which actually depend on the primary key. For example, if A depends on B and B depends on C, A will indirectly depend on C, which is called transitive dependency. It is not direct nor partial dependency. In partial dependency, the attributes depend on the primary key, but are not fully dependent on it. But here, we have no composite key, so we can call it transitive or indirect dependency. Back to our table. Another problem is that if we change the name of the author, we also have to change the date of birth of the author. Date of birth depends on the author, because if we change one attribute, we also have to change another attribute. To solve this issue, we have to see that author and book are different entities. They relate or depend on each other, but they both are different entities, which is why they have to exist in separate tables. So if we separate the author table and the books table, and because the relationship between them is a one-to-many, that's because one author can write multiple books, we can break them into separate tables, and then we can combine or join them by using a foreign key. As you can see on the screen, I separated the authors table and the books table, and added the information of authors in the author table, and the information of books in the books table. I used author ID in the book table as a foreign key, which helps me recognize the book and the author of the book. To summarize, something we faced in the different forms of normalization were issues of data duplication, or problems where we didn't keep the different entities in separate tables. When you design any database, make sure to differentiate between entities, i.e., teacher is a separate entity, a student is a separate entity, a course is a separate entity, an exam is a separate entity, a book is a separate entity, etc. So make sure you don't mix up these entities and make separate tables for them. Also, you need to make sure that they all relate with each other, So the next step is that you need to clarify the relation between entities, as well as what kind of relationship is formed between them. One-to-one relation, one-to-many relation, or many-to-many relationship. Once you have figured this out, you can define and organize your data in the database. If we follow these guidelines, we won't have any problems in our database. When you keep the entities separate, the rules of normalization will be followed automatically. It eliminates the risks of partial dependency and transitive dependency. For example, if we have products and customers, they are both separate entities, and they both need to exist separately. But it is obvious that there is a relation between them, because customers will buy products. This is why we need to figure out the relationship between them and make separate tables for their relationship. In that case, we could make a table of sales to provide information on customers and the products sold to customers, where only the related information of products and customers will be added. If you organize and separate your data and entities properly, the database should be normalized automatically. Just to repeat myself, first, you have to figure out how many entities you have in a database. Second, make separate tables for each entity, then figure out the relationship between them. Third, organize them properly and don't mix entities or data with each other. Welcome to this lecture, where we will discuss how we can design our database. At the beginning of our lectures, I told you that our query's execution and other actions could be useless until we learn how to design a database properly. If we are working on a big business or any big model, we need to know how to design a database. For now, I will use the example of product supplies. So, how we can create a database of a product supplies type business. For this purpose, we will select some entities which are the following. Number 1, suppliers. Number 2, customers. Number 3, addresses. Number 4, products. Number 5, customers' orders. Number 6, customer addresses. Number 7, ordered products. Number 8, cancelled orders, and number 9, payments. We could add more entries to this list, but let's keep our database design rather basic. One more thing. We will use tools to design databases, which you need to add to your SQL. In this lecture, I will use Lucid to design our database. We will search for Lucid Database Tool on Google, and then open the website Lucid Chart. This website is related to charts, and we can make any chart or diagram by using this website for free. They also have a premium version if you want to work professionally. I am already logged into this website, and I have already created a small database. Let me show you the database I've created quickly. This is the chart, as you can see on the screen. Of course, you can edit this according to your requirements. It just requires a simple account setup with your Gmail account. You would just need a few more details to complete the setup, which is why we want to use it. As you can see on the screen, it shows a premium plan, but I'm just using a simple free version. If you want to purchase the premium version, you can purchase it. The chart on the screen displays my recent projects. If you want to make a new chart, then you have to click on New, which you will find above the Home button on the left upper corner. Click on the Lucid chart and then click on Create Form Template. The website will give you options, depending on your purpose for using this website. So if you choose other categories, then the template options will also change. Because I used it for database, it shows data-based diagram templates Let's open database diagrams. You cannot use all of them at once. 3 of them are free, and other templates require the premium membership. I will choose the 3rd free template, and my data is loading. As you can see on the screen, the database template has opened, and it is showing some fields. You just have to drag and drop to add your entity tables on the chart. You will also find some tutorials to help you use these tools. So, this is how you set up an account on Lucid. Now, as you can see on the screen, you just have to import the fields 1, 2, or 3 according to your database requirement. After importing them, you can change or edit the entity name by double-clicking on it. If you want to highlight its header, then you have to click on Shaded Header, and you can choose any color you want. The option of color change is also available on the top of the side, as you can see on the screen. If you want to increase rows, you can easily do this by clicking on the field option. The number of things you can add appears on the navigation map. Now let's move on to the main point. We designed this database, but what was the motive? The motive to make this database is to make relationships between entities. You know what relationships are, because I have explained them in previous lectures. As a quick reminder, you can make one-to-one, many-to-many, or one-to-many relationships, whichever is possible for you. On the screen, I have the entities of supplier, customer, products, addresses, etc. Now, we see a relation can be made between the supplier and the customer and the order, the customer address and the product as well. But we will focus on the connection of supplier with customer. That's because when the customer places an order, it will be received through the supplier, creating our relationship. To do so, we drag the line from supplier and import it to the customer line, as you can see on the screen. The line connects them. You can also see some signs on both ends of the line of our entities. These signs also have a specification. You can also change these signs. Basically, they are here to signal the different kinds of relationships between entities. The default sign on the line tells us that one supplier can sell products to many customers. If we use the double line sign, it means the minimum supplier will be 1 and the maximum suppliers will be 2. Basically, using these signs, we can make different relationships between entities. If we use the +0 sign, it means that the minimum supplier will be 0 and the maximum suppliers will be 1. You can explore the other signs to get to know the details of each of them. Unfortunately, I can't talk about all of them in this lecture, because it would be too long. Now let's move back to the relationship we made between the supplier and the customer. In this relationship, 2 suppliers are dealing with many. Now let's focus on the customer entity and figure out with which entity the customer entity can make its relation. We can guess that a relation can be formed between customer and products, customer orders, and customer addresses. I also use a foreign key and highlight it. I have previously explained these concepts, so I refer you back to my previous lectures. Now we will form the relationship of customer with products. The signs on the line you see mean that one customer can order many products. Now we will edit the line and add another sign. This sign means our maximum is many and our minimum is 1. We will also add another sign to our customer, meaning that maximum will be many and minimum will be 0. Now we will form the connection of customer with customer order. This relationship is similar to the relationship between customer and product. In the next step, we will form a connection between customer orders and ordered products and the cancelled order entity. Let's drag the line from customer order to cancelled orders. The sign means the customer order is one and cancelled order can be many. We can also make a connection between products and payment done by the customer. Now let's form many-to-many relationships and add minimum and maximum limits. This means the customers can buy many products and the payments can also be many. By using this method, we can use different relationships. We can connect the address with customer address because we have some specified results. But further addresses can also be added. Now, just drag the line between address and customer address. There can be one address or many addresses. So, you see that we can make different relationships by designing them in Lucid. If you have different projects and make different databases, you will get more experience from it and you will understand the designing process in a better way. You can also search on Google what and how many kinds of databases you can make. There are also examples of databases, so you can practice your designing skills on them. The most important thing is that you can also get the source code of the database we made in this lecture. For this purpose, you have to click on Export, and because we are using SQL, we will choose SQL Server. If you look on the screen, all the queries related to our design appear. And if we copy and paste this query and run it in the SQL Server, the database will be created automatically, without having to execute another query. So that brings us to the end of this lecture. I hope you learned more on how to create databases by using online tools and how to create relationships between your different entities.
In this lecture, we will talk about how we can use union, intersect, and accept keys. Union, intersect, and accept keys are also used to join tables, but there are many special things in it that we can display. For example, when we use the intersect key, we can display the data of two tables in a single table. When we use the concept of joined, then we can display two tables in different frames, where the details of one table appear and details of another table also appear. Or, we can also select specific columns, but then their formation becomes different. If we want to check data of many columns into one column, what should we do for it? Let's open a new query and select our Books table. Select Star from Books. As you can see on the screen, I selected all the tables that I have created in the Books database. I almost created 6 tables, and their data appears below. In the Books table, we have titles. In book_detail, we have titles with further details, and in the third table, we have names. The fourth is completely empty. We will remove this empty table from our query. And in the fifth table, we have customer names, and in the last table, we have usernames. Now, I will target the celebrity, sales, and school tables and remove the other 2 tables above. We run the following query. Select star from celebrity, select star from sales, select star from school. 3 tables are displayed now, and we want to merge name, username, and customer_name in one column. In other words, we want to display the name of 3 tables in one column, and we will have records in 33 rows. We will use the union key to display the data of 3 or more columns from different tables into one column. We will execute the following query for the desired result. Select star from celebrity, union, select star from sales, union, select star from school. If we execute this query, it will cause the following error. All queries combined using a union, intersect, or except operator must have an equal number of expressions in their target list. This error occurred because I didn't select my column. To solve this error, we will remove union from our query and instead run the following query. Select open square brackets name, close square brackets, from celebrity, union, select open square brackets customer underscore name, close square brackets, from sales, union, select open square brackets user underscore name, close square brackets, from school. The result will display the combined data of 3 columns in 29 rows. Now, if we execute the query without using union, as follows: select open square brackets name, close square brackets, from celebrity, select open square brackets customer underscore name, close square brackets, from sales, select open square brackets user underscore name, close square brackets, from school. It will display the result in 33 rows. When we used the union in the previous query, it displayed the result in 29 rows. Why do we see a 4-row difference? Actually, these rows are not missing. There's a difference because the names that were similar in the 3 tables are only displayed once. However, if we use union all, like in the following query, select open square brackets name, close square brackets, from celebrity, union all, select open square brackets customer underscore name, close square brackets, from sales, union all, select open square brackets user underscore name, close square brackets, from school. If we execute this query, it will display our result in 33 rows, which means it also displays those names which are the same in the 3 tables. If you have thousands of names and you want to check which names are similar, then you use the Intersect key. It takes the form of the following query. Select open square brackets name, close square brackets, from celebrity, intersect, select open square brackets customer underscore name, close square brackets, from sales, intersect, select open square brackets user underscore name, close square brackets, from school. Here, we don't have any results, which means that there are no identical names in all 3 tables. Now, if we execute the following query, select open square brackets name, close square brackets, from celebrity, intersect, select open square brackets customer underscore name, close square brackets, from sales, it is not displaying any result, which means that there is no repeating name in these two tables. Let's try with the following query. Select, open square brackets, customer underscore name, close square brackets, from sales, intersect, select, open square brackets, user underscore name, close square brackets, from school. It will display three names: Ali, Carlos, and Peter. This means that these three names are similar in both tables that were mentioned in the query. Now, if we execute the following query, select, open square brackets, user underscore name, close square brackets, from school, union, select, open square brackets, name, close square brackets, from celebrity, it will display 15 names. Now, we will delete the last three rows in a query. If you want to check your data by only targeting one table, you can use the except key. We need to run the following query. Select, open square brackets, name, close square brackets, from celebrity, except, select, open square brackets, customer underscore name, close square brackets, from sales, except, select, open square brackets, user underscore name, close square brackets, from school. Now, if we execute this query, it will only display those names which relate only to the celebrity table. It could be any table, but in our query, we specified the celebrity table. We use the except statement to filter records based on the intersection of records returned via two selected statements. The records that are common between the two tables are filtered from the table on the left side of SQL except statement, and the remaining records are returned.
In this video, we will look at the SQL index. The SQL index can be used when we want to retrieve our data very quickly and want to make our query fast. More specifically, we will see how we can create an index, and we will also talk about the different types of index. Index and its types. So, let's start. A common example which is used to understand the index is the index of a book. Why do we use an index in a book? We use an index in a book because if there wasn't one and we wanted to search for a specific topic in the book, then we would have to go through every single page of the book until we found the topic we were looking for, which is very inefficient and time-consuming. However, when an index is used in a book, then every topic mentioned in the book will be listed in the index, with the page number in which to find it. For example, if I have a book on physics and I want to research kinetic energy, then I will just go to the index of the book and find the page numbers which talk about kinetic energy in the book. If the index is not given, then I have to go through every page of the book until I find what I'm looking for. Another example would be in the library. In the library, books are arranged in a specific order that facilitates finding the book we need easily. Imagine that the books in the library are arranged in alphabetical order. If I want to search for a book that starts with the letter A, then I will go directly to the A section and ignore all the other sections from B to Z, because I know that the book I'm looking for will not be in these sections. When we talk about arranging data, it means that our data is sorted, just like we saw with our example of books in the library. it's quite obvious that searching in our data that is sorted is easier than if it isn't. If you've learned about data search, then you must know that we can do binary searches on sorted data. There are many searches available which help us find certain kinds of data very rapidly. But if the data is not sorted, we have to go through every record before finding our desired record. Previously, we have talked about the example of the library, in which we said that books were arranged in an alphabetical order. What if we wanted to find a book from a specific year? It is quite obvious that physical books can be arranged in alphabetical order, or can be classified according to the name of the author and other categories. We can arrange them yearly according to dates of publication. But we cannot arrange books in all orders at the same time. It takes time to sort physical books according to one order, and we can't mix them up as we please. This is where databases come in handy. If we wanted to find a book through another search method than the one displayed at the library, we could store the names of the books in a software, allowing us to arrange them in another order. Let's suppose I wanted a book which was published in 2011. I would search our database, which is sorted according to the year of publication, and check the section 2011. Now, let's suppose that we find the desired book and its name starts with H. Because books are physically sorted in alphabetical order, now we will just physically go to where the H section is located and find our book. So here we've seen two methods of arranging data. First, the books were physically arranged in alphabetical order. And the second method meant that we didn't have to physically sort books, we just stored the record of our books in a register and sorted it according to our convenience. The benefit of this is that we are sorting books in multiple ways, and we don't have to arrange the books physically. We can easily sort the books in multiple ways logically because we have a register, and we can create any type of indexes in it. These are two arrangement methods. We also have indexes like this in a database, but these were just basic types of indexes. Another kind of index is the clustered index. A clustered index specifies the physical order in which the table records are stored. There should be only one physical order, because you cannot arrange books in multiple physical orders. A book can exist in only one form at the same time. In a database, we can also have a clustered index, which defines the structure of a table, which is the order of the data as it is stored in our hard drive. A clustered index should be sorted, and it defines the structure of the data which is directly stored in the hard drive. After this, we have the non-clustered index. Non-clustered index. In a non-clustered index, the data is not stored physically, but we will make another reference table where we sort our data according to our convenience. We just refer to the original table with the help of a pointer. A clustered index is faster than a non-clustered one, because if we want to search for a record, we also have the data in the hard drive that is physically available in the same form. If you want to search data from a non-clustered index, you have to search from a second table, and then you will have to locate the record in the original table. Another thing is that there is only one clustered index in a table. This is because the original data is stored in a disk, making it the only structure possible. If you wanted to make multiple structures, basically, we would be creating a table by creating multiple duplicate copies of one table. We don't want to do that, so that's why our tables only have one clustered index. but we can make multiple non-clustered indexes. This doesn't mean that we need to use an index on every field we want to search for with efficiency. Because an index has cause is data that should be in sorted form, otherwise the index will not work. If we insert a new record, then the index will be rearranged because the new value which is entered has to be arranged in the index again. That's why it takes time. So updating and inserting statements becomes slower and slower when we increase the number of indexes. That's why you should try to keep your indexes as few as possible. Use the indexes that are necessary in the database, but don't use extra indexes. Otherwise, updates and inserts will be slower. Now, we will see how we can create indexes in the SQL Server. We will run an index query. We will write create and then mention index and then write IX. We will also write IX here and then we will add an underscore and then write any name we want. For now, we will write index name. We will place it in the sales table for now, but we could use any table. We also have to mention a column. For now, we will add the name column. The query is not displaying any result and is saying that this column doesn't exist. Let's select the sales table to check our column names. As you can see on the screen, column underscore name is the name of a column now. So we will mention this column name in the query as follows. Create index IX underscore customer underscore name on sales open brackets customer underscore name close brackets. We will execute the query. It will not show any result in the table. We need to go to index to see the result. If you want to delete or drop the index, you have to run the following query. Drop index IX underscore customer underscore name on sales. If you execute this key, your index will be deleted. We can also check one more thing here, which is that the index which were created was added on our primary key automatically. If I show you the sale index, as you can see on the screen, the clustered index is formed on the first primary key I had set. At the start of our lecture, I talked about clustered and non-clustered indexes. As you can see on the screen, a clustered index is automatically formed on our primary key, but I created a clustered index with the name customer underscore name, which is not a primary key. This is why it appears as non-clustered and not really unique. You could bring uniqueness to it by adding some things, but for this lecture, we will stop here.